of Grassmannians consisting of highly cyclically symmetrical points. And the paper is basically written, I can send you a draft if you want to see it. I'm trying to prove one last thing that I'll explain towards the end, and so I haven't posted it yet. Okay, so the talk is takes place inside the Grassmannian, which is the set of k-dimensional subspaces of an n space, an n-dimensional complex vector space. And that's a projective subvariety of some projective space. And the embedding goes as follows. If I have a k-dimensional subspace, I can pick a basis. Each basis vector I think of as a row vector, and I stack them together to get a k by n matrix that represents my subspace. And from that k by n matrix, I can calculate n choose k numbers, all the k by k determinants of that matrix. And those numbers are called the Pluker coordinates of the subspace. And in fact, they characterize the subspace, and they're well defined, meaning I chose a basis over here, but when I change the basis, all I do is rescale all the Pluker coordinates, which doesn't matter in projective space. Okay, so writing down this 2x4 matrix, I've told you a point in Gr 2, 4, namely the span of its rows. And this matrix has 6 Pluker coordinates, 4 choose 2. So for example, the 1, 3 minor, I calculate this determinant, which is 1. So delta 1, 3 is 1. And so on. And I've color-coded here according to which Pluker coordinates are equal and which Pluker coordinates are not equal. So in particular, delta 1, 2 equals delta 3, 4 for this particular point in the Grassmannian. Likewise, delta 2, 3 with delta 1. Okay, and I said I wanted to study highly cyclically symmetrical points. So with respect to what notion of cyclic symmetry, so the Grassmannian has an automorphism, which I denote by rho. They're called the cyclic shift map or the cyclic shift automorphism. And what it does is if you have a k by n matrix, you just cyclically rotate its columns. With a little detail that when you wrap things around modulo n, you introduce a sign. And this sign is chosen so that this sentence is true. When I cyclically shift, all I do to Pluker coordinates is add 1 to every index, modulo n. Okay, and the definition, the main definition in this talk today is the Elf Fixed Locus. So it's the set of points in the Grassmannian which are fixed by rho to the L. So at the moment, it's just a subset of the Grassmannian. So symmetrical with rho to the L symmetry. As an example, this matrix which I showed you above, I calculated its Pluker coordinates, and I pointed out to you that certain Pluker coordinates were equal to each other. And this is exactly the ones you need to be equal to each other to be fixed by rho squared. Because 1, 2 maps to 2, 3 maps to 3, 4 under the cyclic shift map, and so on. And a different way of saying this is that this matrix and this matrix, so which I got by cyclically shifting the columns 2 units, even though they look quite different, they have the same Pluker coordinates, which is kind of a strange property. They have the same row span. So some preliminary remarks. It's easy to see that if I cyclically shift n times, I haven't done anything. So this is an automorphism of order n on the Grassmannian. So we're really working in a cyclic group, finite cyclic group. And that means that to study all L fixed loci, we might as well just study the ones where L divides n by taking GCDs. And in particular, my notation henceforth is that n always factors as r times L, and I'm studying the L fixed locus. So r is the order of rho to the L. And in particular, I'm claiming that the n fixed locus is just the Grassmannian. And another technical point, not very important to me today, but just wanted you to think about this, is that saying that a point is L fixed does not mean that rho to the L acts on its Puka coordinates trivially. So it's allowed to rescale the Puka coordinates by an rth root of unity, because Puka coordinates are in projective space. You're allowed to rescale them. That scalar doesn't need to be 1. Why study this object? I have 3 answers. So first of all, and there's this interest in the combinatorics community in this phenomenon called the cyclic setting phenomenon. And how it goes is you have a cyclic group acting on a finite set. And you want to count symmetry classes with respect to the cyclic action and give nice formulas. And there's kind of a general philosophy for how you should do this. And it's an interesting question to try to do this when you have a cyclic group not acting on a finite set, but rather on a space. And it's not clear what the correct statement is, probably about Euler characteristics, but what kind of, how should the formula look? And I think this is kind of the first example you should look at, because I can calculate everything in sight. And then the game is just to find what the right statement is. And that's something I have not solved. I want to work on that in the next few months. Another reason I got interested in this question is that Stephen Karp already thought about it. So Stephen proved that there are exactly n choose k row fixed points in the Grassmannian. So if you're just trying to study points fixed by the generator or by the cyclic shift map itself, that's already an answered question. There are n choose k of them. And you might be more familiar with the statement that there are n choose k torus fixed points in the Grassmannian. Those correspond to the vertices of the moment polytope. And there's a precise relationship between these two things, these two statements. Basically, the discrete Fourier transform on C to the n, the ambient space, takes torus fixed points to row fixed points. And lastly, these spaces turn out to be kind of related to type Muir theory and generalized cluster algebras in this work of Chekhov and Shapiro, and I think there's more to say about that. And that'll be towards the end of the talk. Okay, so what kind of theorems do I want to show you today? So I'll show you 4 theorems. All of them are, I'm going to show, describe the Elf Fixed Locus from 4 different perspectives. So the first perspective is kind of complex geometry or algebraic geometry. Is this an algebraic variety? What's its dimension? Does it have components? What's its degree in the Pluker embedding? Is it smooth? Things like that. Is it a familiar variety like a Schubert variety? Secondly, I want to study rho to the L fixed points from the perspective of total non-negativity. So I want to describe all points in the Grassmannian that are rho to the L fixed and have non-negative Pluker coordinates. So for the Grassmannian itself, there's a very nice cell decomposition. Does the same statement hold when you work cyclically symmetrically? So another famous thing about the Grassmannian is that there are these nice total positivity tests. So you can check that all Pluker coordinates are positive by only checking a very small subset of them. Does that statement still hold with respect to symmetry? And lastly, is there some kind of cluster structure on this space of cyclically symmetric points? Maybe let me pause for 30 seconds in case anyone has any questions. Okay, so the first theorem I want to present talks about the complex points. So as a warm-up, the one fixed locus in the Grassmannian, I told you, Stephen Karp proved, is just a bunch of points. N choose k points, it's a 0-dimensional space. And on the other side, the n fixed locus is just the Grassmannian itself, a smooth, irreducible, projective variety of dimension k times n minus k. So there are 2 extremes. We have a 0-dimensional variety and the Grassmannian itself. What variety interpolates between these 2?
Oh, sorry, Chris, I'm slow. May I ask, some question?
Yes.
If you take L equal n, So
Yes.
you just have one fixed point, right?
L equals n means you're shifting by n units, which does nothing.
That's nothing. Oh, okay.
It's just the Grassmannian. So L equals 1 is some points. L equals n is the whole Grassmannian. L equals some intermediate number will be some, subvariety.
Yeah, right. Oh, sorry, yeah.
Yeah, so really, you work in Z mod NZ. So L is in Z mod NZ.
Yeah, right. Sorry, yeah. No, basically the question is if you consider the case like, well, when you have points, yeah, are there any kind of optimal properties that one can characterize these points? Like what some function which take minimum or maximum on these points?
Yeah. So I'm not sure I could state something off the top of my head, but Stephen's paper is only 5 pages long, and he shows it's like critical points of the potential on the Grassmannian and.
Okay. So there is potential on Grassmannian such that it's critical.
Yeah, and the critical points are these cyclic shift, and there's other interesting. These n-choose k points are special from a few different perspectives.
Thanks. Yeah.
Okay, so the theorem is that is a description of this space. Oops, it's a description of this space for any L. So what it says is that the space is typically disconnected. It's a union of many Richardson varieties in the Grassmannian. So a Richardson variety in the Grassmannian is just an intersection of a Schubert variety and an opposite Schubert variety. One way of setting this up is a Schubert variety, you pick a basis and you kind of do Schubert conditions from left to right. And then an opposite Schubert variety, you use the same basis, but do Schubert conditions from right to left. And then you intersect those two Schubert varieties and you get a Richardson variety. And that involves a choice of basis. And the interesting thing is that kind of the components of this space are not Richardson varieties with respect to the standard basis that you start with when you talk about C to the n. Instead, it's you have to kind of do the Fourier transform. So they're Richardson varieties with respect to kind of in a weird basis, the basis of eigenvectors of this matrix rho to the L. So you think of rho as being an n by n matrix that implements the cyclic shift map, and then it has eigenvectors, and you work with respect to that eigenbasis. Okay, so anyway, this variety has many connected components, each of which is a nice variety, a familiar variety, a Richardson variety. And the components are labeled by k multisets of the numbers of the multiset 1 to the L dot 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 R to the L. So we have two parameters always. L, which is, we're studying rho to the L symmetry, and then R, which is the order of rho to the L. And those two parameters give you a multiset, and then you take k multisets of that multiset, and that's the number of components. And in particular, once you know all this stuff, it's kind of easy to just write down anything you want about this variety. In particular, it's a simple calculation that the dimension of the variety is given by this formula. So roughly speaking, since you're working modulo rho to the L symmetry, and that has order R, you should be squishing down the dimension by a factor of 1 over R, which is kind of what it looks like. But that won't even always be an integer, so there has to be some correction. And kind of interestingly, the correction factor is the size of a smaller Grassmannian. So beta is always less than R, and this is the size of some other Grassmannian, and you subtract off the size of two Grassmannians and divide by R, and that's the dimension formula. And anyway, okay, so since we know everything about Richardson varieties, we know everything about this variety. And as small examples, so the one fixed locus, as I told you, is just n choose k points. And by my theorem, it's supposed to be indexed by k multisets of the numbers 1 to the 1 dot 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 n to the 1, which is just n choose k, the number of k subsets of 1 to the n. And for the Grassmannian itself, how it works out is you're supposed to look at k multisets of 1 to the n. And, well, there's only one of those. Okay, so that's the end of the discussion of what the points look like. It's a bunch of Richardson varieties. Okay, the second theorem has to do with total non-negativity. So a reminder, a point in the Grassmannian is called TNN, totally non-negative, if all of its Pucher coordinates are non-negative real numbers. And this gives you a subset of the Grassmannian, the totally non-negative points. So some background, which you may or may not be familiar with, is that the space is very nice topologically. So first of all, it has a cell structure, CW decomposition. And the cells in the CW decomposition are specified by saying that I want exactly these Pucher coordinates to be positive, and I want the rest to all be 0. So sometimes, I mean, if you make a stupid choice, you won't get any points this way. But if you get a non-empty set of points, it's automatically an open ball in Euclidean space. That's what Postnikov proved in some Euclidean space. And so it's natural to ask, well, how many cells do I get? And what's the topology of the face complex of the CW structure? And the answer is that cells can be naturally labeled by a lower order ideal in the Bruhat order on the affine symmetric group. So here I've tried to draw Bruhat order on the affine symmetric group. This is the identity permutation, and things keep going forever. And the cells are just a funnel at the bottom of that Bruhat order. That's how many cells there are. And the closure order on cells, saying when I can go from one cell to another by taking a limit, is exactly just Bruhat order, or rather it's dual. And the dimension of a cell is just the length, the Coxeter length in this Coxeter group. And lastly, the whole space is homeomorphic to a closed ball. So all of the TNN points taken all together at once is a closed ball, and it's a full dimensional ball. So this ball sits in the Grassmannian, and it's a ball of the same dimension as the ambient variety. Okay, so that's kind of classical stuff due to many authors, especially Postnikov, and then the ball statement is due to Goloshin, Karp, and Lamb quite recently. So let's say that's the description of the N fixed locus. What's the description of total non-negativity for the 1 fixed locus? Well, Stephen Karp proved that there is exactly one row to the fixed totally non-negative point. So out of the n choose k points, there's kind of a very special one that's totally non-negative. Okay, so my next theorem interpolates between these two statements. So the theorem says that just as before, if you look at row to the L symmetrical points that are totally non-negative, again, there's a CW structure. So, and again, you do it in the same way. You say, I want these Pucher coordinates to be positive and the rest to be 0. And it's surprising but true, or it's something you have to prove, that you still get cells in this way. So that topologically, such a thing is an open ball. And how many cells do you get? What is the natural parametrizing set? So I claim that it's a lower order ideal, again in an affine Bruhat order. But in this time, if you're working row to the L symmetrically, you work in the affine symmetric group on L symbols. So if you want to study like row cube symmetry, you work in S tilde 3. And it's kind of interesting because in the previous statement, you would think of this as being associated to like Gr KL. And you know, for Gr KL, you'll get some kind of small order ideal. But if you want to study this object, you'll get a much larger order ideal in the affine Bruhat order, but it's still the, you know, it's still the right kind of combinatorics. And then all the same statements hold. Cell closure order is Bruhat order, cell codimension is Coxeter length, and the entire space is a closed ball that's full dimensional in the ambient variety. So basically all these theorems are well behaved under considering cyclic symmetry classes. And as a corollary, which I want to emphasize is not trivial, it's surprising. So suppose I take a bunch of K subsets and I say, I want to make these Kluger coordinates positive and the rest 0. And suppose the conditions I impose are rho to the L symmetrical and come from a totally non-negative point. Then I claim that there actually is a symmetrical point in the Grassmannian that has that satisfies those conditions. So the assumption is just about K subsets being, you know, symmetrical. And the conclusion is about points in the Grassmannian having equal Kluger coordinates. So equality of real numbers, like 6 = 6 and 3 = 3 for my first example. And so that's not obvious, and in fact, it's false for other matroids. It's a special property of positroids. So it's quite easy to find an example of a realizable matroid that's symmetrical, but does not give rise to any symmetrical points in the Grassmannian over R. Over C, probably not. So anyway, this is a non-trivial property of totally positive points, is that symmetrical matroids give rise to symmetrical points. And by the way, why is this true? It's because I proved above that it's a cell. It's not only non-empty, it's a cell. It's, you know, a lot of points. Okay. So that's the description of total non-negativity. Now I'll move on to total positivity tests. Okay, so as background, what's the usual story? The usual story is that for the Grassmannian, there exists efficient total positivity tests. So what do I mean by efficient? What do I mean by total positivity test? So let's say we want to test if a point in the Grassmannian is totally positive. Well, the dumb way, or the usual way you would think, is just to calculate all of its Kluger coordinates, of which there are n choose k many. But it turns out that, in fact, you can just test a small subset of Kluger coordinates, ratify that they are positive, and conclude that all Kluger coordinates are therefore positive. And what I mean by efficient here, my technical definition is going to be that the size of the total positivity test is 1 larger than the dimension of the ambient variety. And the 1 larger comes from the fact that, like, the Grassmannian is in projective space, and somehow you need to work in affine space, and so you add +1. Okay, so what about for the 1 fixed locus? I told you there's only 1 totally non-negative point. And an efficient test, it's a 0-dimensional ambient space, so supposedly it would consist of 1 Kluger coordinate. And 1 Kluger coordinate basically has no meaning. And it definitely will not be true that out of the n choose k points, I tell you 1 Kluger coordinate, and you can say, oh, it's the totally positive point. So it's kind of not very clear what the right generalization of this statement is to the 1 fixed locus. Does the 1 fixed locus have efficient TP tests? Okay, so my theorem is that yes, all Elf fixed loci have efficient TP tests. And there's kind of an important technicality. So the first part of the theorem is mostly just an observation. It says that, so as I mentioned in theorem 1, the Elf fixed locus is a bunch of Richardson varieties, disjoint union of them. And amongst all of those, there's a distinguished one called D, mathcal D. And that distinguished kind of positive component contains all of the Tn endpoints. So Stephen proved the same statement for the one fixed locus, right? There's a unique, totally non-negative point. And I'm saying that the same thing is true. There's a lot of components, but exactly one of them is like the totally positive component. And so I claim that the right statement is that you should only try to do TP tests for points that are in that connected component. And if you do, then everything works out correctly. So if you give me a point in this special component, this Richardson variety, I can test whether or not it's totally positive efficiently via a total positivity test that has the right size. So what I'm trying to say is that you can't use Pluker coordinates to tell which connected component you're in. That's too much to ask. But if you know you're in the right positive component, then the same story generalizes. And what's a little bit striking to me about this statement is that you can prove it for all values of the parameters, K, R, and L. And that's tricky because, like, you know, symmetry kind of cares a lot about divisibility properties of the numbers. You know, how symmetrical things can be depends on if certain numbers have, you know, a factor of 3 in common or whatever. But anyway, all the number theory kind of works out, and the statement is just generally true. And I can show you a small example that will show you kind of the sense in which this is non-trivial. So let's just try to study total positivity tests for Gr28, where I'm imposing row squared symmetry. So as I'm guessing the whole audience knows, total positivity test for Gr2n, yes, such a test can be encoded by a triangulation of an n-gon, or an octagon in this case. And the first thing I want to point out is that you can't triangulate the octagon in a way that's row squared invariant. I don't know. I don't know how you maybe prove such a thing, but it's obvious. Just try it. So in this example, I've drawn kind of the best you could possibly do. It's a partial triangulation. So this partial triangulation is row squared invariant. And then to complete that partial triangulation to a full triangulation, you have to make one of these two choices, neither of which can be made in a rotationally invariant way. So let's say we took this one, delta 1, 5. Well, what I want you to notice is that these two are actually in an orbit, so they're equal to as functions on this space, they're equal to each other. If your point is row squared invariant, then this Pluker coordinate equals this Pluker coordinate. And now you apply a skein relation or a Pluker relation. You see that this thing squared is equal to this thing plus this thing, but those things are all equal to each other also. So you end up just getting this relation. And therefore, the positivity of this arc implies the positivity of the extra arc that we didn't want to add, this guy. Except there's a caveat, which is that, well, really, I took a square root when I argued that, so I could have taken the minus sign, which is a little bogus. Actually, the positivity of this does not guarantee the positivity of this. It guarantees the non-zero-ness of this. But on this special connected component that I was in my previous theorem statement, you can prove that you always take the positive square root, not the negative square root. And therefore, it is indeed a total positivity test. So that's why this kind of mumbo jumbo about connected components is an important assumption. And the assertion is that this procedure works in general. So I can exhibit, by a nice construction, highly symmetrical clusters for the Grassmannian, meaning as symmetrical as you possibly could get, which I can precisely state. And then these won't need to be completely symmetrical, and you just delete the non-symmetrical guys. So in this case, you delete this guy if you added him, or delete this guy if you added him. And then you can prove that the leftovers are an efficient TP test of the exactly correct size. And a remark is that this construction actually works for all cells, not just for the top cell. So for positroid cells, not just for the Grassmannian itself, if you care about such things. Okay. I'll pause for 30 seconds again. Okay, so the last the last theorem I'd like to talk about has to do with cluster algebras, and this is the Msu cluster structure. So cluster algebras need no introduction, I hope. A well-known statement is that the coordinate ring of the Grassmannian is a cluster algebra. I think this was proved by both Gene Scott and Chekhov-Shapiro. So to specify a cluster structure, you need to describe some initial seeds, and here's an example of an initial seed for Gr 3.8. It's Gr 3.8 because I have the numbers 1 up to 8 appearing. These are all Pluker coordinates, by the way. I've just written 135 to mean delta 1. And then it's Gr 3 because there are 3 numbers in the Pluker coordinates. Okay, and so in blue are the cluster variables, and in red is the quiver. And on the outside are the frozen variables. And as a reminder, what's the purpose of the quiver? It encodes some neighboring cluster variables. So if I want to mutate at some cluster variable x, then there's some binomial in the numerator, and then I divide by the variable I'm trying to replace. And as an example, let's say we were trying to mutate this guy. Well, the binomial here comes from these two, the guys that point in. The binomial here comes from these two, the guys that he points out to. I divide by 134, the guy. And I assert that although this looks like a maybe you could mute all of us and I can unmute myself. Okay.
Oh, I think it's work. Yeah.
Yes. Okay. Okay. So this mutation looks like it produces a rational function in Pluker coordinates, but the kind of miracle is that actually it's a polynomial Pluker coordinates. It equals delta 235. And you can check this by just clearing denominators and seeing that you have a Pluker relation in this case. Okay, so I want to develop a similar story for rho to the L fixed points. Okay, so my goal is to obtain a cluster structure on this distinguished component, the positive component, inside the Elf Fixed Locus by a folding construction. Like the way you fold a type A Dinkin diagram to get a type B Dinkin diagram. Okay, and so maybe one comment. So a cluster algebra is always an irreducible variety, or cluster variety is always irreducible. Cluster algebra is always a domain, an integral domain. And so you really need to work with just the positive component, not with the whole Elf Fixed Locus. So here's what I'm trying to say. So for Gr 3.8, I've chosen a very symmetrical cluster. I'm working mod rho squared again. And so that means that this Pluker coordinate equals this Pluker coordinate equals this Pluker coordinate equals this Pluker coordinate, and so on. And I've highlighted in purple a fundamental domain for the symmetry. And you might hope that you can just take this nice cluster and fold it and get a cluster structure on the subvariety. So this does work for this variable. So if you write down his exchange relation in terms of the purple variables, you get this. So this guy equals this guy, so it becomes this guy squared. And then the other guys just are already purple, so no problem. So it looks like we're in business, not so bad. But there's a problem when you try to do the same recipe to this variable. So this variable has a bad feature, which is that there are variables pointing into him which are equal to him, right? This is an orbit of the rotational symmetry. So if you write down the exchange relation naively, it looks like this in terms of the purple variables. And you get a cancellation. This cancels with this in the numerator and denominator. And so you're left with not like a nice Laurent polynomial mutation. You're actually just left with a sum of two current cluster variables. And that's definitely not a mutation. For example, mutation is supposed to be a change of coordinates. And here we're not changing coordinates. We're deleting a variable and expressing him as a sum of two current variables. That's not a change of coordinates. It squishes down the size of the field of functions. Okay, so it looks like we're stuck. And I'd like to explain that actually there's kind of a general procedure to fix this problem, maybe ideologically. Okay, so the fix has to do with generalized cluster algebras. Yeah, maybe before I start, so in general, it's not a good operation to fold a cluster algebra along a finite group of symmetries. And I'm suggesting that there is maybe a fix to this. So the part of the story of the fix is there are these things called generalized cluster algebras, which are, I think maybe they were kind of noticed by Grassmannian-Shapiro and Weinstein by a calculation. And then Chekhov-Shapiro kind of wrote them down and developed the theory and proved the Laurent phenomenon and finite type classification. So the sense in which they are generalized is that the numerator, when I mutate, no longer needs to be a binomial. It's allowed to be a polynomial. There are certain conditions on what kind of polynomials you're allowed to take, but anyway, there's a precise definition. And these have showed up in nature a little bit. So there's some connection with WKB analysis, with representation theory of affine SL2 at roots of unity, quantum affine SL2 at roots of unity. Grassmannian-Shapiro and Weinstein have given kind of like lots of examples having to do with GLN. And so, my theorem in a second is going to be that you can find such a structure when you work cyclically symmetrically. And some motivation for this comes from Teichmuller theory. So a really well-known story in cluster algebras is the story of cluster algebras from surfaces. So Fomin, Shapiro, Thurston. And geometrically, that has to do with decorated Teichmuller theory of a marked surface. And there's a very nice kind of cluster algebra interpretation of things. And mutations are these things called Ptolemy relations. So cluster variables in this setting correspond to lengths of some arcs with respect to a hyperbolic metric. And the Ptolemy relation is some statement about lengths inside a quadrilateral. And this well-known story bears two generalizations, which are less well-known, but quite well-known also. One is due to Falcon-Goncharov. You can study higher Teichmuller theory of the surface, which rather than just depending on the surface, it also depends on a choice of a semi-simple Lie group, G. And again, we kind of moduli spaces that arise in that theory have a cluster algebra structure. But the other way you can go is you can make your surface a little bit more complicated by like working with orbifold points of some order R. And when you do this, you don't get cluster algebras naturally, you get generalized cluster algebras. And when you try to mutate an arc nearby an orbifold point of order r, the exchange relation that shows up, the mutation, is no longer binomial, but rather the numerator is trinomial, and it has this kind of interesting trigonometric number, 2 cosine pi over r, where r is the orbifold point, order of the orbifold point. Okay, so I think it's an interesting kind of question to ask, like, can you complete this diagram? So what is like an orbifold Ptolemy relation that depends on the group G as well? So the higher technical theory version of this relation. And I think the correct answer has to do with Elf Fixed Loci and Grassmannians. So basically, the calculation that Chekhov and Shapiro do to get this relation has to do with triangulations of an n-gon, which is Gr2n. And so instead of working with Gr2n, you should just work with Gr_kn. And that will be the SLK generalization. Okay, so here's my last theorem of the day, and then I'll just do a little bit of discussion to end the talk. So as usual, I'm assuming that I'm studying the Elf Fixed Locus in Gr_kn, where n is r times L. And an important point, which is kind of annoying, but it's just the way life is, I think you have to take the parameter r to be at least as big as k. So I think if you do not make that choice, you will not get cluster structures of any type. Instead, you might get some really weird thing that is not axiomatized yet. But provided you take r sufficiently large, then there is a generalized cluster structure. Let C be an efficient TP test for the positive component, as I described in my previous theorem, theorem 3. So to remind you, those things are constructed by you pick a really symmetrical cluster for the Grassmannian, you delete the things that aren't the variables that are not symmetrical, and then the leftovers are what you want. Okay, so I claim it. Such a thing gives rise to a generalized seed in this algebra of functions on this positive component, this Richardson variety. So for all but one of the variables, the mutation rule is just the rule you would write down naively by folding, as I was showing you above. And the same thing is true. The picture is always that there's kind of like an inner orbit of bad variables, and then outside that inner orbit, everything is kosher. And for the special variable, the mutation rule is kind of the usual type of generalized cluster algebra thing. So you construct two monomials, m minus and m plus, which are the monomials pointing into and out of the bad variable, the special variable, except you delete the special variable from the monomials. And then there are some coefficients. And the kind of interesting miracle to me, or I find it very interesting, is that the coefficients are these kind of really non-trivial trigonometric numbers. So a big, oh, I wrote pi, it's probably pj, sorry. So it's some crazy product of signs, just like we saw in the SL2 orbifold Ptolemy relation, which had a cosine of pi over r. So these numbers are always positive, but they're a product of many, many sign evaluations at rational multiples of pi. And maybe I'll state the theorem as saying that all neighboring variables lie in this algebra of functions. So all one-step mutations yield regular functions. So what I'm asserting is basically that this exchange relation holds in the coordinate ring. So I believe something stronger is true. So I believe that this provides this algebra of functions with an upper cluster algebra structure. And the reason I haven't put the paper up is I'm trying my best to prove as much of that statement as I can. So I'm able to prove it in certain cases at the moment. So for example, whenever you have a completely symmetrical cluster, i.e. you don't have to delete any kind of extra non-symmetrical variables, then I can prove the statement by an unfolding type of argument. And I have other approaches too, but like they're still being thought through. So back, returning to our example, how should you write down the exchange relation for this variable? It wasn't very clear from folding, and I claim that the correct answer is that this is how you should mutate him. This quadratic polynomial, or cubic polynomial with 4 terms in the numerator, and some sign evaluations. In this case, actually, it's all multiples of pi over 4, so all of the signs are maybe 1, or maybe plus or minus 1. But that's just because R is 4 here. In general, R can be anything, so this will be interesting trigonometric numbers. And what I'm asserting is that this, which looks like a rational function in Pluker coordinates, magically, when you work modulo the relations and you work modulo symmetry, is actually just a polynomial in Pluker coordinates. So here's an aside which I really like, and I think is, to me, really explanatory. So say you take any quiver and you pick a vertex of that quiver. Something you could do is just glue a bunch of copies of that quiver along the distinguished vertex by an oriented cycle, as I've done here. So I added these blue arrows. 5 copies in this case, but it doesn't really matter. And now you want to fold. So you treat all of these variables, all of these letter B's, as being the same variable, and you mutated them simultaneously, and so on. So it's clear how to mutate all of the variables A, B, C, and D. What's not clear is how to mutate the variable V. If you fold, it doesn't look good. Well, what I claim is that there's a correct answer to this problem. So what you're supposed to do is you should perform the DT transformation to this subquiver, to this cycle. So the DT transformation, or if you like, the green to red sequence, or whatever, is some explicit sequence of mutations that most quivers have, and you do it. And what I claim in this case is if you do it, then you just get out a generalized mutation. Chekhov-Shapiro generalized mutation of degree n+1, or with n+1 terms. The only kind of sticking point here is that there are no coefficients. So the coefficient string is all 1s. So if you want to get more complicated things, I think you need to kind of have interior variables, not just the in cycle, but put some interior variables and make them satisfy some relations. And I think you can get all Chekhov-Shapiro relations that way. So, which is just to say that I think that generalized mutations can be unfolded to ordinary mutations by a recipe of this style. And my last remark is just that there exists a close relationship between this cluster algebra structure I described above and one that Gekman and Shapiro and Weinstein have discussed on band matrices. So I'm in the middle of verifying this. It requires calculating some determinants, which I can't yet calculate. So I can do it when k = 2, and when k = 3, I'm already unable at the moment. So that's the end of the talk. Thank you.
Okay, thank you. Thanks, Chris. Any questions?
Sorry, I have a quick question. So in the end, you mentioned the DT transformation. Is it an involution in that case?
Well, it is an involution if you make all the variables equal to each other. Otherwise it, sorry. It's an involution, I think, even when you don't make. Because if you look at the model of a once punctured disk, it's the transformation that changes tags at the puncture.
But in that case, actually, you have to rotate this by a certain angle as well. But I think it's right. So because all the variables here are the same,
are equal to each other. Right, yeah. Right. So it would not, yeah, but by a detail. I mean, it's a variable permutation, but yes, you're right.
Okay, thank you.
Yes.
Chris,
Yes.
Since you mentioned connection to band matrices, so this coefficients was signs that you presented. So
Yes.
can you naturally write them down as coefficients of characteristic polynomial of some?
Well, that's what I'm trying to do at the moment.
All right. Okay.
It's when k equals 2, it's already pretty hard, and k equals 3, it's like really, really difficult. But yeah, these things that you call in your paper C tilde I of x, y,
Right.
I think amazingly specialize to just being numbers in this case. So I wrote a little example. So oh, I've unpaired. Let me show you real quick. Sorry, it'll be a second. Okay, here's an example. So this is some kind of matrix of Pluker coordinates, and it has a deformation parameter t, which you guys call lambda over mu. And you need to establish that modulo a bunch of relations, it's a product of frozen variables times a polynomial with constant coefficients. Right. And the constant coefficients are like signs.
Okay.
I can do it when k equals 2, and I can't do it yet. Okay.
Yeah. All right, but yeah, that looks exactly like the kind of determinants. Yeah.
Yes. Right.
Right. Thank you.
Yes.
Volodya?
Yes, so I have, well, a few short questions. So yes. First of all, can you say something about symplectic properties of this stable set?
No, what kind of, so like, is it closed, you mean? Like,
for example, well, yeah, it's Lagrangian or, well, isotropic or co-isotropic or whatever. It's just some subsets of Grassmannian with symplectic structure, well, the general symplectic structure. So the question is what's...
Yeah, no, thank you for the question, but
there is also a related question, maybe, I don't know if you, that, you know, if you have a stable points under an automorphism of cluster variety, then you can associate to it, well, an element of K3 or equivalently some number, which is in case of three-dimensional manifold, it's just hyperbolic volume. So there is some distinguished number, well, or group associated with stable points of this, for example, or if it's not stable point, but it's a component, so to every component, so associate some number like hyperbolic volume. So the question is if you have something computed, something in this particular case, or...
No, what's a reference for that construction?
Good question. Well, any text by Sasha concerning this K2 symplectic structure.
Yes.
This will be there. Well, I can tell you, of course, it's very simple story.
Yes.
Well, we can talk later. I'll explain how to work. It's related to the symplectic structure directly. It's just a kind of more involved. And also about reference, I just like to ask you a reference about the story about cells, correspondence between cells and these affine permutations.
Yes. You mean just in the usual Grassmannian?
For usual Grassmannian,
yes,
or for your case as well. Mm-hmm.
Well, my case, I guess I'll put it on the archive soon, but it's not. I can email you the current draft of my paper.
That's your construction.
No, I mean, in cyclic symmetric setting, it's my construction, but in the usual setting, it's not the way Postnikov wrote it. So the reference where they explain this clearly is due to Knudsen, Lamb, and Speyer.
Mm-hmm.
It's called juggling patterns or something.
Okay, but so they don't use the notion of affine permutation, or? No,
they do.
I see.
But Postnikov did not. Yes.
I see. Juggling. Okay. And this concerns really the cells you are speaking about are the cells in the real setting or in
yes. Yeah, you consider real non-negative points.
I see. And for cells in cell decomposition for complex points. It's
you can also study the variety, breaking it up into kind of subvarieties, and they're labeled also by the same cells. And
okay.
each of those
And there are also cells, or just cells in the sense that
yeah, they're not affine spaces. They're
not affine spaces.
Smooth subvarieties, but not affine spaces.
Thank you.
I have
and
up to Volodya's first question. So this one shift map, this map rho is a Poisson map on the Grassmannian.
Right. So automatically it's
well. So you're looking at fixed points of some of some Poisson. Well, it's not involution, but Poisson that has whose certain degree is identity. So there must be something.
Yeah, but it doesn't say in, well, yeah, of course, but it's a rather symplectic mapping, because here you have symplectic structure, not Poisson.
Serежа?
I have a question. Hi. Toward the very end, you described an unfolding procedure, right? I mean, you first stitch several copies of a quiver with an oriented cycle, and then you say you explain how to describe the generalized cluster structure.
Yes.
And then you said that this shows that this type of structure can be embedded into an ambient, bigger one, from which it is obtained by unfolding.
Yes.
So in your running example, if you apply this, do you just recover the Grassmannian, or do you get something intermediate?
I think you get the Grassmannian. Yes.
Did you try to? Do you always, like, if you get some stable point, invariant?
Yes.
Invariance of some cluster automorphism, and then apply your construction, and then unfold, do you always recover what you started with, or do you sometimes recover something? You see what I'm asking, right?
Yeah, it's a good question. So it seems to me like the arguments are pretty soft, but like I've mostly been interested in the implication. I know the cluster algebra upstairs, and I'm trying to prove the Laurent phenomenon or whatever for the cluster algebra downstairs. I haven't thought very hard about the reverse direction.
About going the other direction, right?
Yes.
And do you know of any interesting examples of Chekhov-Shapiro algebras arising in life which are not obtained via this type of folding?
Well, I'm kind of thinking that the answer should be no, but I think I'm kind of hoping over the next few days to learn all these examples and, say they come from some cyclic action, but yeah, that's just a guess. I don't know. For
so
example,
this would somehow
roots of unity quantum affine algebra 1, I'm guessing probably arises this way. That's
okay.
Other questions? If not, I have like in your theorem 4. So what goes wrong when R is less than K? So
yeah, So the kind of thing that happens is that you have maybe a variable. Let me think a few seconds. Okay, I'm not sure how to draw the quiver at the moment, but the kind of thing that goes wrong is you're trying to mutate X, and on the right-hand side, maybe you have a common factor of Y.
Okay. So okay.
So the right-hand side is divisible by one of the variables.
Yeah, I see.
And it seems like it's not so bad because everything comes from folding. So there's a finite type example where you can still just blindly mutate and you get like a nice closed, kind of hexagon or something like that.
But expression in bracket is irreducible, right? Or what? So my question is,
bracket is irreducible.
Can you divide by y and this standard trick?
It didn't. I mean, Pasha and I thought about it. It didn't seem like it was.
It's exactly what happens in Teichmüller theory. So when you have this.
Right. Yeah. But this is like it's not a frozen variable or anything. I don't know.
No, you don't need frozen variable to do it.
Frozen variable. That's true. I don't know. I should think about it. Yeah.
Thanks. And another kind of, I don't know, question, remark that I ran recently into paper by Agranovich, who considered like critical points of the following function. You take a function on Grassmannian, which is the ratio, well, real Grassmannian, the ratio of the biggest Plücker coordinate divided by the smallest one.
Yes, right. I also
think that they're exactly like, well, they should be related to your critical points that you consider. And
yeah, that's probably true.
I just wonder, so if you take the flow, gradient flow with this function, does it give like, well, maybe another proof of this ball construction? And yeah,
right.
so
yes.
was wondering. So do you know anything about that? So
no,
maybe a simpler version of the kind of potential function or something.
Yeah, there's probably a relationship. One thing in Stephen's paper, he works with a version of the cyclic shift where you add a parameter. Sorry, where is it? Here. You add a parameter t in the last column. I wonder if this allows you to flow, you know, taking t to 0 or something.
Maybe, yeah. Okay. And I have another question from Alyosha Rosli, who had to leave, but he wondered what software you use to do your slides.
Oh, Good Notes?
Oh, Good Notes. Okay.
Yes.
Thanks.
Yes, absolutely.
Okay. Any more questions? If no, so let's thank Chris for a wonderful talk. And yeah, please, yeah, if possible, send me your slides. I kind of posted, well, another time, independently on you. It will be safe for future generations.
Well, mine will be deleted by the end of the day, so.
Okay.
Thank you.
Thanks, everyone, and see you next week. Bye-bye.